In today's video, we will understand working principle behind a steam turbine. Steam turbines are considered to be the heart of the power plant, because this is the device which converts thermal energy from fluid to mechanical energy, more precisely as rotational energy of these rotors. So series of such rotors, which eventually absorb the fluid energy, by virtue of its rotation, are the most vital component of a steam turbine. So, let's have a close look at one of such rotor set, in order to understand more about its working. Here it is. This is one rotor set, and you can see there are series of blades which are connected to hub of the rotor. And in different orientations it will look like this. Or, like this. If you take a close look at one of such blade, you can observe one thing. This blade is a collection of different airfoil cross-sections set together. Airfoil cross-sections which vary in size and shape from bottom to top. When high-energy steam at inlet, the steam with high pressure and temperature flows over such a blade, it will induce a pressure above and below the blade. And thanks to the special shape of the blade, the pressure above will be always less than pressure below. So, there will be a resultant net force acting in upward direction. This force will make the blade rotate, in this manner. As the blade rotates, it obviously absorbs some energy from the fluid, so fluid at exit will have lesser energy compared to inlet. In coming session we will see how we can predict the energy transfer in fluid. But before moving to that, we will have a brief look at energy associated with a flowing fluid. There can be three components of energy for a fluid. First, due to its velocity, the kinetic energy part. Second, virtue of its pressure, the pressure energy. Third component, virtue of its temperature, the internal energy. Last two components of energy, pressure and internal energy part, can be combinedly called as enthalpy. If a fluid is having a high enthalpy value, it obviously means it is having high pressure and temperature. Now we will see exactly how a steam turbine is absorbing energy from steam. This is the rotor cross-section of blade, at a particular length. As the steam passes over the blade will rotate in this direction. And this will result in energy loss to the fluid. For a typical steam turbine, both kinetic energy and enthalpy part come down. So if you plot velocity of steam from inlet to outlet, it will be like this. As kinetic energy decreases, velocity decreases. Similarly, enthalpy also decreases, like this. Now the next step is to pass this steam to next stage of rotors. But if you directly pass steam to another set of rotors, it won't absorb much energy, because here velocity of steam is already very low. So before passing the steam to next rotor, you should increase the velocity first. For that, we will use something called nozzle, a stationary device which is attached to casing of the turbine. They are also called as stator. Stators are also a set of blades, but these blades are stationary. It won't take part in energy transfer. What it does, it simply transform energy from one form to another form. Or more precisely, it will transform the enthalpy energy into kinetic energy. You can see the cross-section area of nozzle decrease with flow, so due to its special shape the velocity increases. But at the same time enthalpy decreases. If you sum change in enthalpy and kinetic energy, there won't be any change. Now we have increased velocity of fluid, so we can put next set of rotor. Again stator. And again rotor. So in a steam turbine there will be alternating sets of such rotors and stators. Rotors which are moving attached to the hub. Stators which are stationary, attached to the casing of turbine. Now, we will have a close look at energy transfer at rotor. If you sum kinetic energy and enthalpy energy change across the rotor, you will get total energy transferred. What could be the contribution of each of these terms? Is it possible that enthalpy energy change is zero, still the kinetic energy part contributes to the energy transfer, or vice versa. This is defined in a term called degree of reaction, which is defined like this. So value of degree of reaction could vary from 0 to 1. Suppose for a turbine degree of reaction is 0, then such turbines will be known as impulse turbines, or 0% reaction turbines. In such cases enthalpy energy change across the rotor will be 0, and energy transfer will be purely due to kinetic energy change. Blades of an impulse turbine will look like this. Here fluid actually hits the blade and produce the force. Or force is produced on blades due to pure impulse action of steam. We know along the blade enthalpy doesn't change. Along with enthalpy temperature will also remain same, because enthalpy is a direct function of temperature assuming steam as an ideal gas. There will be slight drop in pressure, but you can almost assume pressure is same across the rotor. The only quantity which changes here is the velocity. Now, the other extreme case. The 100% reaction turbines. Here, as you guess, there won't be any kinetic energy change across the rotor, energy transfer will be purely due to change in enthalpy. And this could be typical blade profile for such a case. Here fluid passes through the blade without actually hitting it. We know, across the blade there is no kinetic energy change, so absolute value of velocity remains same across the blade. But pressure, temperature and enthalpy vary across the blade. A practical steam turbine will be a compromise of these two cases. People usually use 50% reaction turbine, known as Parson turbine. That is all about working of steam turbines. Thank you for watching the video.